Hi, in this lecture we are going to investigate some of the different kinds of forces that we will be studying in this course. First of all, let's reinvestigate or reintroduce ourselves to gravity. So gravity, as we know, is a contactless force acting on any object which has mass. Okay, so this is a pull kind of force, which means it pulls other masses. So gravity is a force that exists between any two masses, anything which is massive. So it will exist between you and me, and you and your book, you and your chair. Every massive object is pulling other massive objects with the force of gravity, and it doesn't require any contact between them. Okay. However, ask yourself why you don't really feel yourself being pulled to a friend when you two are speaking in close proximity. Think about that. And physically, we give gravity the name of weight. So what is weight? Weight is the force of gravity on any massive object. W, or weight, also can be denoted by F sub g, equals mass times gravity. M times g. G is 9.8 meters per second squared near the surface of the earth, but it can be different for different places like the moon or other planets. Gravity is also the force responsible for our existence in general, because it is the force that keeps all of the planets in orbit around the sun. So without gravity, we wouldn't be here. There wouldn't be any earth circling the sun, and without the sun there would be no life form. Let's move on and talk about another kinds of force that we have not formally met before in this course. This is called tension. Tension arises when you attach a massive object to a rope or a string or anything like that. So what it does is, if you attach another mass to a rope or a string, the rope or string always pulls the mass. So that is just its general reaction to hanging a mass to it. So this pulling force we'll call tension, and it exists in any rope mass system. For example, elevators, or a mass or a ball hanging at the end of a string which you play with. Let's look at an example of how we denote tension. So let's say this is a rope and we have attached an object to it. The free body force diagram will look like the tension force pulling the mass upwards along its length, and the weight will always be there whenever you have a massive object. So we are considering that the rope is massless, which we will mostly consider in this course. But when you hang a massive object that you are not neglecting to that rope, the rope pulls along its length, while gravity will act from the center of this massive object straight down, which we term weight equals mass times the acceleration due to gravity. Alright, let's look at an example of gravity and tension at work. So here we have a frame or a sign that is hung on a wall. Okay, so maybe the person hanging it is a huge office fan. You would know what Schrute Farms is. And then the frame is hung at the angles shown. The angles are to the vertical. So one string is at an angle of 30 degrees, while another string is at an angle of 15 degrees. And we want to find the tension in each of these strings, considering them to be different strings. So what would be the case if they were the same? Well, if the strings were the same, then the tension would be the same. Okay, so our goal is to find the tension in each of these strings, and given to us is that the mass of the frame is 2 kilograms. All right, so first of all, we must draw the free body force diagram. So the first step is, let's draw the FBD. We have the box here. Before drawing the forces, let us first choose our axes. I will choose plus x going this way, plus y going upwards, and on this diagram we will have to denote all the forces. So first and foremost, since this frame has a mass, it will have a weight of mass times g. So mass is 2 kilograms times g. G sometimes we might mistake as grams, but this g is the acceleration due to gravity. So 2 times g means 2 times 9.8 on Earth. Okay, now let's look at the two strings. Let's look at this string first. So with the vertical y-axis, this string is making an angle of 30 degrees. And let's call the tension force. The tension force, remember, will be pulling this frame along the rope or string, okay, in both of these strings. So let's call this T1. Okay, this is T1, and the other force is due to the other string attached at an angle of 15 degrees to the vertical. Okay, let's call this T2. All right, this is our free body diagram. What is the second step in doing Newton's second law problems? And we will do Newton's second law problems whenever we are asked to find the tension or any kind of force in general, and also in most cases when we combine kinematics and dynamics, we might also use Newton's second law to find acceleration. Okay, so as we meet more problems in further lectures, we will know much more about how to evaluate these types of questions. So here, since directly it's asking for a force, the tension, we will, without any question, write down Newton's second law first of all. Actually, second of all, because first we draw the free body diagram. So Newton's second law, let's remind ourselves what the statement was written as summation of all the forces was equal to the mass times the acceleration caused by the resultant force. Okay, now these are vectors like we have done with other problems previously. So the next thing is we have to remember this summation of f means that we are summing over vectors. So we have to be very careful about the direction of these vectors. Specifically, we will only sum x components of vectors to x components of other vectors and y components of vectors to y components of other vectors. So since some of these vectors, specifically T1 and T2, are at angles weirdly than our usual horizontal and vertical notion, we will have to first break these two forces down into their x and y components. Let's go ahead and do that. For this, the y component would be along the y-axis, the x component would be along the x-axis. So y component can be either positive y or negative y. Similarly, x component can be either positive x or negative x. So let's find that. Since this is our chosen axis, if we consider T1, then we can see that it is going to the left horizontally and is going to the up vertically, right? Because it is that kind of force on this coordinate system. So the x component would be along this direction and the y component would be along that direction. Okay, so this is T1y and this is T1x. Okay, similarly, this T2 force is now a force like that, and so it is the x component is going to the right as the vector moves along. The y component is going up as the vector moves along. So the y component is like so, pointing upward in the positive y direction. So we have the x component pointing along the positive x direction and the y component pointing along the positive y direction. We call this t2y and we call this t2x. The next thing we have to do is we have to find the components. So since this is a triangle and we know this angle with the vertical, that must mean any other angle which is here also with the vertical component would be 15 degrees. Similarly, if this is 30, this is my vertical component and this is the force, so any other angle with this same force on the vertical will also be 30 degrees, and we know that this is 90, this is 90, so that we have a right angle triangle. If this is 15 and this is 30, our job then is to find T1x and T2x. So what is T1x? T1x is this force right here. So if you consider this triangle, this is my opposite and this is, let's write T1 here for convenience and T2 here for convenience, in that T1 and T2 are magnitudes of the total tension force in that particular string. So since this is a right angle triangle, we will use this right angle triangle. This is my opposite, that is my hypotenuse. So when finding T1x, we are relating opposite and hypotenuse. That should mean we have T1 times sine 30. T1y, this component right here, is relating adjacent because this has both the right angle and the angle on the y component side. So T1y is the adjacent and T1 is the hypotenuse. So it is relating adjacent and hypotenuse. That means it is T1y is equal to T1 cosine 30. Similarly, we can also find out T2x. T2x is T2 sine 15. T2y is equal to T2 cosine 15. Okay. Now that we have all our components, it is time to write down our x and y Newton's second law equations. Let's first go for x. What is the x equation? We will sum all the forces in the x direction and set that equal to mass times the acceleration in the x direction. Hence, what is the summation of all the forces? Let's consider what are the forces we have in the horizontal direction. We have T2x and we have T1x. Okay, so this force and that force, no other forces are horizontal. So T2x is going in the positive x direction, hence a positive sign in front of it. T1x is going in the negative x direction, so a negative sign in front of it, minus T1x is equal to mass times acceleration in the x direction. Now this frame is not said to be moving, it is just said that the frame is hung. So when a frame is hung, it is basically stationary at that point unless you choose to move it. Since it is stationary, we can directly say that it has no acceleration. So both components of acceleration, x and y components, is 0. So on this side we have 0. What is T2x? T2x is T2 sine 15 minus T1x is T1 sine 30, and that is equal to 0. We can subtract either of these terms from both sides and we end up with, let's say we end up with T2 sine 15 on this side and we are adding T1 sine 30 to both sides. So we have T1 sine 30 on the right hand side. We don't know either T1 or T2, so this equation is not enough for us to solve our problem. So what we will do is we want to eliminate one of the unknown variables to make our life easier. So let's say we want to eliminate T2. So what we will do is we will solve this equation of two unknowns for T2. So let's keep T2 on this side and divide both sides by sine 15, and we end up with T1 sine 30 divided by sine 15. Let's call this equation 1. Now let's make some space so that we can work out our problem more clearly. Now let us write down the y Newton's second law equation. So summation of Fy is equal to MAy. Ay is 0 like we talked about. So what do we have in the y direction? We have three forces in the y direction. We have the weight, we have T2y, and we have T1y. So let us sum those. So T1y and T2y are both pointing upwards, that is positive y direction. So we have T1y plus T2y, but weight is pointing downwards, so negative y direction. So negative w is equal to ma, which is 0 because ay is 0. Then what is T1y? It is T1 cosine 30. What is T2y? Plus T2 cosine 15. What is w? It is 2g, so minus 2g equals 0. Okay, so we have another equation with two unknowns, 1, 2, and we have to eliminate one of those to make our life easier. How will we eliminate? So we will realize that from equation 1 we have a solution for T2 in terms of T1. So if we use this expression for T2, that is equation 1, we can eliminate T2 from this equation as well. Then we would only have one unknown, which is T1. Let's do that. So everywhere you see T2, replace T2 with this whole expression. Let's go ahead and do that. So we have T1 cosine 30 plus T2 cosine 15. T2 is being replaced by T1 sine 30 over sine 15. It is multiplied with cosine 15 minus 2g. G is 9.8, so 2 times 9.8 equals 0. And another subtle point about calculating weight is when we consider the gravitational force as the weight of a mass, this g can be considered to be just the magnitude of the acceleration. So because you're already using your vector concept to say that gravity or weight is directed downwards, so you don't need to include a negative g when you're calculating weight. Okay, this is somewhat different from when we were working with kinematics and considering vertical acceleration g. Okay, so maybe a little bit confusing, but you will get used to it. All right, now we can see that we have only one unknown in this whole equation. Let's make some more space. So let us separate out T1 terms and everything else on the other side. So let's keep T1 terms on the left hand side. So we have T1 cosine 30 plus T1 sine 30 over sine 15 times cosine 15, and then add 2 times 9.8 to both sides of the equation. So we will have 2 times 9.8 on the right hand side, and we realize that we can choose to factor out T1 from these two terms because they both have T1 in it. If we do that, we'll end up with cosine 30 plus sine 30 cosine 15 sine 15 equals to 2 times 9.8. So what is our goal? Our goal is to find T1. So we divide both sides of this equation with this whole thing. What does this whole thing come out to be? This whole thing is cosine 30 plus this term, which is 1.87, and remember to keep your calculator modes in degrees, not radians, and this is 14.9. So if we divide out both sides by cosine 30 plus 1.87, then we have T1 equals 7.16 newtons. So this is the total tension, the resultant tension, or the total tension in string 1. Okay, then we want to find T2. What is T2? T2 can be written in terms of T1 using equation 1, as we have done. Just wherever you see T1, replace T1 by 7.16. So then T2 becomes 13.8 Newton. So T2 is the total tension in string 2. So this was the picture, right? So this was T2 and this was T1. Okay, and T2 was subtended at a smaller angle than T1, and we found the magnitudes of T1 and T2. It turns out that T2 has a bigger tension than T1. So why? Because T2 is at a higher angle, that is at a smaller angle to T1. What does that mean? So the smaller you make the angle with the vertical when hanging something from a rope, the more tension the rope will pull at. Okay, so if the string is completely vertical, then tension is maximum. If you relax the string and increase the angle with the vertical, then you have less and less tension. Okay, I hope this makes the concept of gravity and tension working together a lot simpler.